Hello and welcome to this talk on landing and internal web pages, the strange case of Jekyll and Hyde in web performance measurement. I am Vakar Akil from Duke University, and my co-authors are Balakrishnan Chandrasekharan, Anya Feldman, and Bruce Maggs from the Max Planck Institute and Duke University. We call landing and internal pages Jekyll and Hyde, but the duality here is not between good and evil, it is between simple and complex. Most of us at some point have measured web pages. Perhaps we wanted to evaluate the effectiveness of a performance optimization, or we wanted to measure the adoption of a security protocol. But whatever the purpose might be, how do we go about actually measuring web pages? Well, the first step, at least in case of active measurement, is to pick one of the top lists such as Alexa Top 1 Million, Tranco, Quantcast, or Majestic. The second step then is to pick a day or a range of days over which the list is downloaded. The third step is to make a subset out of the list. Maybe you don't want to measure all 1 million pages, maybe you want to measure just the top 100,000 or a random sample. The fourth step then is to measure the landing page of each website. And then you go on to analyze the characteristics and trends, whatever you're interested in. Our paper here is about the fourth step. Why do we just measure the landing page? By doing so, we make either one of the two assumptions. We are either assuming that landing pages represent the entire website, or we assume that measuring landing pages is enough and we don't need to go into further pages of that website. If you have done this before, you're not alone. Everybody ignores internal pages. To see if that statement is actually true, we surveyed 5 top networking venues over 5 years. We surveyed ACM-IMC, PAM, Usenix NSDI, ACM SIGCOM, and Conext. Over the last 5 years, from 2014 to 2019, 920 papers were published in these 5 conferences in total. We downloaded all of these papers and automatically searched them for keywords related to top lists such as Alexa. We found out that 119 papers used at least one of the top lists, and upon closer inspection, we found that only 15 of the 119 papers measured internal pages in some way. The rest, 104 papers, completely ignored internal pages. We manually reviewed those 104 papers to check if the results reported in those papers would need to be revised if they were to apply to internal pages besides the landing pages that were actually measured. The findings of our survey are reported in this table. Not so surprisingly, IMC is the venue where most papers that used top lists were published, and we concluded on a subjective scale that 9 of those papers would need major revision to apply their results to internal pages, and 23 would need minor revision. Similarly, PAM is also a heavy user. NSDI, SIGCOM, Conext, they also use to a lesser extent, and their papers also require major or minor revisions as reported in the table. The takeaway from this survey is that 2/3 of the papers that used some top list in those 5 venues, 2/3 of the 104 papers would need some revision to apply their results to internal pages. Researchers measure the landing page because it is easy to do. You get the domain from one of the top lists, and if you follow that domain, it takes you to the landing page of that website, and there's only one landing page, so you're basically done. But if you talk about internal pages, there are thousands upon thousands of them for every single website. Surely we cannot crawl all of them exhaustively for each measurement. So what can we do instead? How do we discover the internal pages and select some of the thousands of internal pages for each website? We have several methods. The first one would be to crawl a website exhaustively and select some pages randomly. The second one would be to go to the landing page and monkey test the website by randomly clicking the buttons, typing text, and following links to internal pages. The third method could be to go to websites such as Twitter, Facebook, Reddit, and other social media websites and collect links to internal pages to other websites that have posted on these social media websites. The fourth method could be to get user metrics directly from websites or browsers that collect them, and discover internal pages based on those. The fifth method could be to go to search engines and search for websites. That will give you internal pages for those websites. After some analysis, we determined that the fifth one was the best one for us because it combines all three of the approaches 1, 3, and 4. Search engines crawl websites exhaustively as well as we can. They count backlinks like Google does for the PageRank algorithm. It counts the links to other websites that have posted on some other prestigious websites. And then they also combine user feedback. As people search for and click on links, that data is accumulated and used for ranking results on search engines. So that is what we used. Using search engines, we built a new top list, a top list of web pages and not just websites or domain names. We call this list the Hisper list. It is named after a glacier in Pakistan. Unlike other top lists, the Hisper list has two levels. The first level has websites, and the second level has a list of internal pages for each website. For the first level, we get websites from the Alexa Top 1 Million. Then, going down the popularity rank for each website omega, we get Google search results for the term site:omega. We go down the Alexa popularity rank and we get search results for about 2,000 websites. For each website, we get 50 pages in total, 1 landing and 49 internal, and we end up with a list of size 100,000 web page URLs. We restrict the search results to the English language and set the location for the search to the US region. We update this list weekly. It costs us about $70 per week to generate, but we provide it to other researchers free to use and free to modify. To get the list and the source code behind it, go to the URL here, hispar.cs.duke.edu. Now let's move on to the actual measurements that we have made on internal and landing pages using the Hisper list. Here I describe the measurement methodology. The first step, we generated a version of Hispar with 20 pages for each website, 1 landing and 19 internal, as opposed to the previous 50 pages per website. Then we made sublists of this list, the top 1,000 websites, H1K, the top 30 websites by Alexa popularity rank, the top 100 websites, and the bottom 100 websites. Then we fetched each landing page 10 times and all the internal pages once each using Firefox on Ubuntu. Every page was fetched with an empty or cold cache and a new user profile. This means that users were not logged in and pages behind login were not measured. For each fetch, we recorded the HTTP archive or HAR file, and then we moved on to analyze the differences between landing and internal pages across 9 different characteristics. We also calculated the statistical significance of these differences using Kolmogorov-Smirnov test p-values. We also added a set of smaller experiments for crawling, ads, DNS, etc. to add more detail to our analyses. Now I talk about our actual findings. The first question we ask here is, are internal pages uniformly different? If they are uniformly different from landing pages, then the differences between internal and landing pages can be corrected by a constant factor, and we don't actually have to measure the internal pages. To answer this question, we used a smaller experiment. We selected 5 websites with different Alexa popularity ranks: Wikipedia, Twitter, New York Times, How Stuff Works, and the MIT academic website. We recursively crawled each website until we obtained 5,000 unique URLs, and then we randomly sampled 500 pages from those URLs for each website. Then we crawled those 500 pages once each, and we crawled the landing page of each website 10 times. Here we plot the total page size of internal and landing pages across these 5 websites. Total page size is defined as the sum of all response sizes in the HAR file. For New York Times and How Stuff Works, we can see some variation in the page size of the landing page itself because there's some randomness involved when the same page is fetched multiple times. For the 3 websites on the right, you can see that there's a large variation in page sizes across the 500 internal pages. On the right, we see a similar plot for the number of objects in internal and landing pages across the same 5 websites. The number of objects is defined as the number of request entries in the har file. Here also you can see a large variation in the number of objects for internal pages. One important thing to note here is that even though the magnitude of the difference between internal and landing pages might change a little depending on which subset of internal pages you choose to compare against the landing page, it is very unlikely that you pick a set of internal pages that changes the direction of that difference. Next, we ask the question of whether the differences between landing and internal pages are completely random. If those differences are random, then they would cancel each other out, and the inferences we draw from just measuring the landing page would stand for the internal pages as well. To answer this question, we use the main experiment described in slide 6. For the 1000 websites in H1K, we get the median size of the 19 internal pages and denote it as i.size, and we subtract it from the median size of the landing page. A negative value then indicates that the landing page had a smaller size than the median size of the internal pages, and a positive value indicates that the landing page had a bigger size. As you can see in the CDF, only 35% of the values are negative. This means that for 65% of the websites in H1K, the landing page had a bigger size than the median size of the internal pages of the corresponding website. Similarly, for the number of objects plot, we calculate the difference in the number of objects in the landing page versus the median number of objects on the internal pages. And here as well, we see that only 32% of the values are negative. This means that for 68% of the websites in H1K, the landing pages had more objects than the median number of objects on the corresponding internal pages. From being bigger and having more objects, one might expect the landing pages to be slower than internal pages. But as we can see in the plot on the right, that is not the case. In this plot, we calculate the difference between the page load time of the landing page and the median page load time of the corresponding internal pages. In this CDF, we see that 56% of the values are negative, which means that 56% of the websites in H1K have landing pages with page load times lower than the median page load time of their internal web pages. This difference is even more pronounced for the top 30 websites in HISPR, where the number changes from 56% negative to 77% negative. Hence, despite being heavier and having more objects, landing pages are generally faster than internal pages. And what's more important, the differences between internal pages and landing pages are not totally random, and we do have to measure the internal pages as well. After comparing internal and landing pages with respect to page size and load time, we move on to more subtle characteristics. We compared the two page types across 9 different dimensions. We divide these 9 dimensions into 2 categories. The first category is content and delivery. In this category, first, we test what portion of a page is actually cacheable. So if a page has more cacheable content, then it will benefit more from CDN edge caching, for example. The next comparison we make is about content mix. We divide the requests in landing and internal pages by the value received in the content type or MIME type header. And we see if the composition of the landing and internal pages is different in that do they have the same amount of JavaScript versus images versus HTML or CSS content and so on. For number 3, we compare the origins from which content is fetched to render a landing or an internal web page. A modern web page may resolve a large number of domain names to fetch content from multiple servers residing on those domains. So here we are counting the number of unique DNS names that were resolved for each category. Next, we examine the inter-object dependencies in landing and internal pages. A web page may have very complicated dependency structure in which object A must be fetched before B is fetched and B and C must be fetched before D is fetched. We also compare the use of explicit HTML5 resource hints, which are meant to help the browser prefetch resources that it's going to need to render the page. For number 6, we compare the amount of time that it takes for individual requests to be served on both landing and internal pages. We also divide that time into steps in the request lifecycle, such as wait, connect, fetch the response, etc. The second category of comparison is privacy and security. For the first point, we determine whether internal pages are delivered over HTTPS or not, and when they are delivered over HTTPS, is there any mixed content? That is, are there any insecure resources mixed in with mostly secure content? Then we examine the number of third-party dependencies on internal pages that are never seen on landing pages. A third-party dependency is an external party from which content must be fetched in order to deliver a complete web page. These third-party dependencies may belong to advertising companies or tracking or some login button, etc. For the last point, we compare the number of ad slots and their sizes and trackers present on internal pages versus the landing page. In the interest of time, we will only go into detail about 3 of the 9 different characteristics. We will talk about content mix, round trip and turnaround times, and HTTPS and mixed content. For the content mix comparison, the question we ask is, are internal and landing pages composed of the same kind of content in the same proportions? To answer this question, we looked at the HAR files from the main experiment. We divided the MIME type of the responses in the HAR files into 9 different characteristics. This plot shows the CDF of the bytes for each category as a fraction of total page size. 3 of the 9 categories, HTML or CSS, images and video, and JavaScript made up the bulk of the pages. The other 6 categories had negligible contributions. As you can see, landing pages in the median have 36% more content in the media category, which is images and video. On the other hand, internal pages have 10% more JavaScript. And they also have 22% more HTML and CSS content as a fraction of total page size. So, landing pages have more images than internal pages do. Perhaps this is one hint as to why landing pages are faster despite being heavier. In this comparison, we explore the performance of individual requests on internal and landing pages. The life cycle of a request is divided into 7 steps. First, the request may be blocked for some time because the browser is busy. The second step is DNS resolution, unless it's cached already. The third and fourth steps consist of TCP and TLS handshakes. Then, send is the time it takes to send the request with any and all headers and data. The sixth step, wait, is the time difference between the last byte of the request being sent and the first byte of the response being received. This is also called the turnaround time. And the last step is to receive all bytes of the response. We observed that although requests on landing and internal pages spend roughly the same amount of time in Connect, landing pages in total spend more time in Connect just because they have more objects served from more servers. More interestingly, requests on internal pages spend more time in the wait step. As this CDF shows, requests on internal pages in the median spend 20% more time in the wait step than those on landing pages. One possible reason could be that objects on landing pages are more popular and hence more likely to be cache hits at the CDN edge. We indeed observed higher cache hit rates on landing pages. So the takeaway here is that requests on internal pages have higher turnaround times. Next, we talk about security. To determine whether a website has a good security posture, is it enough to measure just the landing page? Out of the 1,000 websites in H1K, only 36 have non-secure HTTP landing pages. The rest are served over HTTPS. On the other hand, 170 of those websites have at least one internal page delivered over HTTP when the landing page was HTTPS, and this is only from among the 19 internal pages that we measured. This plot is a histogram of the number of websites, each having a given number of non-secure internal pages. When it comes to mixed content, we found that only 35 websites have HTTPS landing pages with mixed content, but 194 websites have at least one internal page delivered over HTTPS but with non-secure mixed content. We also observed some internal page URLs that seemed to be secured. That is, they started with HTTPS, but they redirected to non-secure pages delivered over HTTP. Hence, if we ignore internal pages when measuring security on the web, we may overlook critical problems. In summary, ignoring internal pages has significant consequences for measurement and for research in general. For page delivery optimizations, it may lead to biased evaluations. For example, improving image delivery will benefit landing pages more just because landing pages have more images. Object prefetching optimizations, such as Polaris, will also benefit landing pages more because they have deeper structure. When it comes to reducing the number of round-trip times in higher layer protocols versus the raw latency, landing pages benefit more from low RTT protocols like QUIC, whereas internal pages will benefit more if we reduce the latency between servers. And as we saw, it may also lead to lapses in security analysis. For example, we don't know of any study on the phenomenon of HTTPS pages redirecting to HTTP pages. Perhaps browsers should issue a warning to users before such a redirection. The last thing I want to say is, for whatever reason you're measuring web pages, please include internal pages in your measurement. You can use Hisper to get a list of internal page URLs at hisper.cs.duke.edu. And with that, I'm ready to take your questions. Thank you.